Pleasure to introduce Brian Metzger, who's visiting us from Princeton University, where he's an Einstein Fellow. He did his undergrad at the University of Iowa and an undergrad student at Berkeley, where he was better as I was expecting to. Brian is soon going to start a faculty position at Columbia University.
So it's a pleasure to be here. This is my first time really spending much time here to see this. It's really good, really nice. So today I'm going to be, well, I should first say, my name is Brian, for those of you that don't know me. My interest is broadly in high energy and stellar astrophysics. One of the kind of overriding themes of my work is interest in time domain or transient phenomena. So events that come and go, sometimes it's explosive events, what we can learn about these events. And in particular, their direct observational signatures. So I think it's really two reasons why it's exciting to be working in transients currently. One is that there's a number of new surveys coming online or are online really across the electromagnetic spectrum. It's a wide field, sensitive surveys. And they're discovering new types of explosions. We already discussed one earlier today, but also many new types of supernovae being discovered. And many of them we don't know what they are yet, and they need explanations. So it's time to, in my opinion, to reevaluate what types of events are happening out there that we know occur that maybe we haven't modeled yet. The second reason I think this area is exciting is that we're entering the era of gravitational wave astronomy. So within the next 5 years, the LIGO and Virgo interferometers will be upgraded to advanced sensitivity. And for the first time, it's very likely that they will directly detect gravitational waves. And one of the most likely sources are the types of Inspiral and Binaries I'll be discussing today. And it's really important that we figure out how to connect the electromagnetic and gravitational wave skies so that we can get the most science out of these detections. So this work I'll be discussing was really done in collaboration with many people and involves a wide range of physics, so their needs here. So just to give you an outline, I'm going to just very briefly overview why I think it's, again, exciting to work in transients now. The bulk of my talk is going to be focused on examples of the so-called known unknowns. So these are the events that we know occur in nature at some rate. We may not know the rate very well, but we know they occur. And for which I'd argue maybe we've not yet unambiguously detected them. It's still tricky. The first example is binary neutron stars or neutron star with a black hole. These events are strong sources of gravitational waves. They may be the central engines of short duration gamma ray bursts. And as I'll argue today, they also give rise to an optical counterpart, which I'll refer to as a Kilonova, which is powered by the radioactive decay of elements that are synthesized in the ejecta from these events. I'm going to focus on what I think is a very important question coming into your advanced LIGO, which is what is the most promising counterpart? And we're going to be able to follow up with gravitational wave detection. On the second part of my talk, I'm going to describe some more recent and speculative work into what happens when a white dwarf merges with a neutron star or black hole. These events have been studied far less than the neutron star mergers, although they may actually occur at a comparable or greater rate. I'm going to argue that outflows from the accretion disks that form these systems may give rise to sublimited supernova of type 1. There are a number of other topics I worked on, which I won't have time to describe, but if you're interested in any of these, please talk to me after the talk. So we've really undergone a revolution in the past few years in terms of rapid cadence wide field optical surveys, really discovering, as I mentioned, new types of supernova, for instance. Kind of leading the way in this regard is the Palomar Transient Factory in California, which has a survey that, it's actually just now winding down, but it has a survey that covered basically a quarter of the night sky every few days to 21st magnitude. It also has a faster cadence survey, at least for very nearby galaxies that are receiving a look for more exotic transients. Pan-STARRS also has a fairly rapid cadence survey that is over a more narrow portion of the sky, but significantly deeper. It's allowed to detect new types of extremely bright supernova that maybe were very rare before, but are now being detected. And I think that the future in this area is bright. At the end of this decade, the Large Synoptic Survey Telescope will be coming online. It's an 8-meter class telescope, again a wide field of view. And its plan is to scan a quarter of the night sky, or sorry, essentially all the visible sky down to 25th magnitude, so every few days. And I think this will really clean up, and the new types of transients being discovered by these surveys will be discovered in abundance by also steep. And they'll have to figure out what to do with all this data. Nevertheless, I think that the outlook is good. And there are a number of other things coming along in the interim. There's new incarnations of PTF and many other surveys. In addition, there's of course the multi-wavelength universe as well. As I already described earlier today, Swift and Fermi have been up there for several years, and they're discovering and new types of events. The radio sky is really opening with all of these dipole arrays being built. Again, wide fields of view, exploring the kind of lower frequency regime, LOFAR and WA. But also, also traditional gigahertz frequencies. There are numbers of small arrays of dishes that I think are really opening the gigahertz transient sky. The types of tidal disruption events we described earlier is one example of what could be out there. We also have all these multi-messenger capabilities. I'll discuss LIGO in a second, but also now HQ is the full sensitivity and even cosmic ray detectors. So let me get into the bulk of my talk and describe neutron-star mergers. So we know of 10 binary neutron stars in our galaxy. Most of these are pulsars. I posted their key properties here. Of course, if you have a binary system, it's a time-dependent quadrupole mode of inertia that radiates gravitational waves according to the period changing according to this formula. Of these 10 of systems, the ones highlighted in red are sufficiently close that they will completely coalesce within a couple of times. The most famous example is the pulsar, which basically confirms this prediction. You can take these QSC systems and estimate how frequently these mergers occur in galaxies like the Milky Way. And although it's highly uncertain because of small number of statistics and corrections you have to make for pulsar beaming, etc., you find that this merger rate is somewhere between maybe 10 and 100 events per million years per galaxy. So the gravitational wave event itself actually comes in basically 3 stages. So there's an initial inspiral stage where the two neutron stars or the neutron star and the black hole are very far apart. This produces a slowly decaying orbit, which produces a gravitational wave of increasing frequency and amplitude. This is known as the Turk. Will actually be this part of the merger that's, at least for neutron star mergers, is detected by LIGO. When the two neutron stars get sufficiently close together, they merge into one central object. Usually, that object is too massive to remain a neutron star, and on a very short time scale, maybe milliseconds or hundreds of milliseconds, collapses into a black hole. As I'll describe later, there may be some evidence that this isn't always the case. There may be some evidence that in some cases this central object can actually survive as a long-lived neutron star. So the hope for detecting this chirp is with the ground-based interferometers, LIGO and Virgo, and there's also now one being constructed will be constructed in Japan, and even one of the LIGO ones will be moved to Austria, or to India potentially. LIGO finished its 6th science run in 2010. It was able to detect these mergers out to a few tens of megaparsecs. Unfortunately, given these small numbers and given that relatively limited volume, it's not that surprising it didn't detect anything. But the real hope for the future is advanced LIGO, which will be at least turning on in the next couple of years. It may take a few years to get up to its sensitivity goals, but when it does, it will be sensitive out to about a distance that's about 10 times larger. So it'll have a volume of sources that's about 1,000 times greater. And so depending on what you take as either the pessimistic or optimistic rate here, you can expect maybe 1 up to several dozen or maybe even 100 of these mergers being detected per year.
Can detect on the spiral system?
It depends on the mass. If the system is 2 neutron stars, you detect the very end of the Inspiral, but not the actual, necessarily the actual merger phase. If it's a black hole neutron star system with a higher mass, the frequency is moving to the LIGO. So for most times, for neutron star mergers, you're mostly detecting the final phase. But it all is happening. It's being detected like 10 minutes or something before the final point. So it's all very rapid. So this will be a great achievement, maybe Nobel Prize winning achievement. But to get the most science out of these events, it's really important that we identify coincident counterparts for many reasons. Obviously, we'd like to put the merger into proper absolute context. We'd like potentially to improve the effective sensitivity of these detectors. So they're trying to pick out this weak signal. If we were to detect a smoking gun counterpart at the position of the consistent with the merger, and we were confident that was the merger, then that would obviously improve the confidence. And potentially you can do other science like cosmology. If you measure the host galaxy and obtain the redshift from the gravitational waves, that gives you some independent sense of the distance from which you could, for instance, constrain the Hubble parameter. So in this paper with Ito, we discussed what we consider to be the 4 cardinal virtues of a counterpart, things you'd like it to satisfy to achieve these scientific goals. Obviously, it must be detectable with what's coming online in the next decade. You'd like it to accompany a high fraction of the gravitational wave events, so you're not waiting around for 10 detections of gravitational waves before you have your first electromagnetic counterpart. And you'd like it to be unambiguously identifiable. You'd like to not be able to confuse it with, say, supernova or something else that could be masquerading as because the important point is that LIGO will be providing error boxes on the sky of several tens or greater degrees. So there's a lot of stuff going on in that error box. So you'd like a counterpart that's pretty unambiguous. And also you'd like to be able to from it localize an accurate sky position so you could, for instance, determine the host sky. So for the mergers, which I think are the most promising source, there's really two types of counterparts that have been discussed in detail. The first is one you've probably heard of. This is the idea of a short gamma ray burst. So the idea is that the merger produces not only a black hole, but an accretion disk around the black hole. And the accretion of that disk through magic or through magnetic field accelerates a relativistic jet. And this is, we know short gamma ray bursts are bright enough that they could be detected after the distance of advanced LIGO. This is great. The only disadvantage of the short GRBs is that we do think that they're relativistically beamed and that the jet has a fairly narrow opening angle. So only if you happen to be looking down the jet axis do you actually detect a short gamma ray burst. So you'd like to complement this with something you could potentially detect from all angles that would accompany your garden variety merger signal. And that's what I'm going to describe as the Kilonova in the second part of my talk. It's something that's isotropic and comes from decaying nuclei. Let's first talk a little bit about short GRB. So I'm going to show you an old simulation. This is by no means recent work, but it gets essential point across showing the merger of two neutron stars. And you'll see the final few orbits of the neutron stars. In this case, they coalesce to a central object which very rapidly collapses to a black hole. Maybe run it again. Let's stop it at the end. There's really two things I just want to point out with this calculation. One is that there's some matter outside the black hole that has too much angular momentum to be immediately incorporated. So it forms a torus. This is a fairly generic feature. Most systems produce a torus. And also that you can get these tidal tails of matter that is basically squirted out the outer Lagrange points during the merger process and may be completely unbound from the system. So people have studied I was talking to earlier, and other people have studied the formation of these Remnant accretion disks, varying, for instance, the mass ratio of the binary, the assumed high density equation of state, in the case of black hole neutron star mergers, how rapidly spinning the black hole is, etc. And depending on these parameters, they find that the mass of this torus can vary substantially. Maybe, in some cases, a very low mass torus, but maybe up to a tenth of the solar mass in more extreme cases. Typically, the torus is fairly well concentrated near the black hole. It's a few tens of kilometers outside the black hole when it forms. So these tori are formed extremely hot with temperatures greater than an MeV. So all of the nuclei that may be composed part of the neutron star are all broken down into free neutrons and protons. It's a very hot torus. It's also very dense, and dense means that the mean free path for photons to get out of the torus is very, very short. The photon diffusion time is very long compared to the evolution time scale of the disk. So it's in a photon trap regime. But it can, and photons cannot cool the disk, so it's generally a fairly thick accretion disk. But it can and does in some cases be cooled by neutrinos. So some people refer to these as kind of neutrino-dominated flows. You can use your standard alpha viscosity estimates to assume there's turbulence in the disk and its transport angular momentum to estimate how long it would take this torus to accrete. And for typical values of the alpha of the disk and the size of the disk, it's typically a fraction of a second, maybe a second. And this means, of course, that these masses in that time scale, it's an extremely high accretion rate. So these are the two motivations for short GRBs. We get this extremely high accretion power, which if we presume it powers a jet. And this time scale, which is actually comparable to the observed durations of short GRBs. So just to remind you, the gamma ray bursts come in two varieties, chiefly distinguished by their duration. There's the long bursts, which typically last about a minute. We have pretty good evidence now that they're associated with the death and mass of stars, both through their association with galaxies with very high star formation, and also, in some cases, we actually see a coincident supernova following the gamma ray burst. So it's pretty definitive that most of these come from dying massive stars. But until recently, or until SWIFT launched, not so recently, but until several years ago, we didn't know anything about the short gamma ray bursts. And the problem was that short gamma bursts had much fewer photons, they had weaker afterglows, they were harder to localize in the sky, and and so you weren't able to determine where they were coming from. But Swift alleviated this. Swift and Teddy 2 actually were the first satellites to localize short TRBs, and they found that they came from very different environments in the long burst. Sometimes they're found outside of elliptical galaxies, sometimes they're found outside or inside spiral galaxies, or galaxies with some star formation, but not as high a star formation rate as the long gamma ray bursts. It's very clear now that the short gamma ray bursts come from a distinct population. They're coming from lower redshift. They typically have lower isotropic energy. And Ido Berger's group has done a lot of work showing that they clearly originate from older progenitor populations. In a few cases where people have looked, there's no detected supernova from the position of the short TRB down to fairly faint limiting magnitude. So this is all consistent with them being mergers. In principle, it could take a long time for two neutron stars to Inspiral, in which case the galaxy could age quite a bit. Yeah?
Could you briefly summarize the argument for why they have been older progenitor conflicts?
It's just because they come from, some of them are in elliptical galaxies, and so the stars and ellipticals are old. So that's the basic. And they're in galaxies. I mean, basically they almost trade stellar mass in the local universe, not star formation. I mean, Ido's argued there's maybe some dependence on star formation, but it's kind of consistent with what you expect from a merging population. This is by no means definitive evidence, but it's all consistent. The timescales. So the one thing that gives me pause when people ask me, are you certain that the short TRBs are mergers, is actually going back to the prompt emission light curves. Many of the short gamma ray bursts are not actually that short. So in addition to the gamma ray burst itself, which you see as this little spike here, lasting a second, many of them are followed by these kind of tails of extended X-ray emission, lasting for 10 to 100 seconds. So these tails are there's significant variability in them, which is not seen in afterglows. It's not thought to be some interaction with the surrounding gas. It's thought to be something coming from the central engine. But it's seen long after the short TRB is finished. And in fact, energetically, it's actually these tails that are seen in about a quarter of the Swift gamma ray burst. Actually, they can have energies coming out of the tails that are up to a factor of 10 or even 30 times more energetic than the gamma ray burst itself. So if you think that the central engine is an accreting black hole, that black hole must be accreting a significant amount of mass on a very long time scale after the merger, which is very difficult to understand. This is, I think, one of the big mysteries is what, we'd like to associate the short gamma ray burst with the time scale of this torus, so what the heck is this extended emission, and why is it so energetic? And what's its second time scale in the problem? There's a few possibilities, none of which I think are definitive that I'll discuss. One I think is instructive, so I'll discuss it. And this is the possibility that maybe it is some type of late time accretion from this disk. Maybe the disk evolves and for some reason the jet shuts off for some period of time, and very late times there's some inflow of mass for some unknown reason. I don't think this actually works, and to show you why this works, we actually did some very preliminary one-dimensional simulations of the evolution of these tori. And the reason it doesn't work is that this torus doesn't survive that long. So if you look at this is kind of just showing you the mass concentration of the torus at various points in time for one of these kind of one-dimensional simulations. So it's a height integrated simulation where it's kind of averaging over vertical height, just showing you basically the surface density of the disk versus radius. So these accretion disks, like many accretion disks in nature, have this kind of property that as they accrete, they actually viscously spread in radius. And this is just a consequence of angular momentum conservation. So if angular momentum as a whole of the disk is conserved, the only angular momentum you're losing is through the inner boundary. So as a whole, it's conserved. So as the mass of the disk decreases, the lever arm of the disk, if you will, increases as the disk spreads. The interesting thing is, as these disks spread in time, it takes, in this case, it was alpha of 0.1, it's spread out to several thousand kilometers in just a second. The temperature in the disk decreases. Something very interesting happens when the disk spreads to about 500 kilometers and its temperature in the midplane decreases below about 1 MeV. And this is that the free neutrons and protons in the disk recombine into helium. And this actually releases a substantial amount of nuclear energy, 7 MeV per nucleon. And given the very extended nature of the disk at which this is occurring, this actually exceeds the binding energy of the disk to the black hole. And furthermore, these disks are only marginally bound anyway because neutrino cooling is not very effective when the temperature is this low. So they can't have no cooling source, but they have this heating source from recombination. And so even from these preliminary calculations, we concluded that a substantial fraction of the disk would be blown away by these kind of thermonuclear powered outflows. And this was actually confirmed subsequently with two-dimensional simulations by William Liedel, where it basically followed the evolution of this disk and followed the recombination. The interesting thing is that maybe a significant fraction, maybe a third of the initial mass of your disk will ultimately be lost in these outflows. So just to drive the point home, if you had no outflows from the disk, the accretion rate would actually decline fairly steadily, slowly with time, and maybe you could get some type of late flare capable of explaining the observed X-ray emission. But if you put these outflows in, the accretion rate falls very rapidly. So I don't think that late accretion from the disk is a viable explanation for these very late flares, unless matter is entering the disk at very late times. And it's hard to get matter to fall back on such a late time to the black hole. You have to think about the dynamical time scale of these systems is milliseconds. So 100 seconds is a really long time. So I'm going to tell you a more speculative idea. And that's the idea that maybe the central neutron star in the merger actually survived the merger process. Maybe it did not collapse into a black hole. Now this requires some combination of effects. One is that you have to have a very low total mass binary so that when it merges, it's not sufficiently massive to collapse to a black hole. It also requires a very stiff equation of state that can support a very massive neutron star. But there is some evidence now that equations of state are stiff from this stuff by Paul Morris, this two solar mass neutron star. And or the actual merger process ejects a lot of material. But say this is possible and say that you're able to keep a long-lived neutron star following the merger, then everything I described will proceed as I explained before. Maybe you're able to get a short gamma reversion from accretion onto the neutron star. But at the end of the day, what you have is a central remnant which is probably very rapidly spinning and probably very highly magnetized, because the amount of the magnetic field strength you're going to generate from the shear during this merger is enormous, 10 to the 15 gauss or larger. And if that's able to produce a dipole field, as Chris has worked on in terms of magnetars, say for instance from a convective dynamo, then you're potentially going to have a strongly magnetized, rapidly spinning neutron star. And that provides you an additional source of energy, this rotational energy of the neutron star, which can come out in a longer period of time. So we did a few calculations to kind of show that this is at least plausible. I did something with Niccolo Bucci-Impini, where we basically put a magnetar wind inside a kind of shell of ejecta, which is the amount of mass you'd expect in these outflows from the accretion disk, and kind of show that even a small amount of ejecta, maybe 100 with a solar mass, is sufficient to kind of collimate the magnetar wind into something like a jet. We also looked at, I've done calculations of the cooling and spin down evolution of magnetars, and using emission models, either internal shocks or reconnection models applied by my collaborators Dimitrios Ioannios, we try to calculate the light curves for magnetars, and they have this kind of hump shape. So this is all just kind of a consistency sense. If you did have a magnetar with reasonable properties, it could potentially explain the second aspect of emission.
There's, of course, the immediate possibility that Shibata has raised, where he's included the thermal component of the pressure in the merger remnant and found that it could stabilize the star for the Kelvin time, even if you erase differential rotation.
But the Kelvin time is pretty short in this system.
I know.
It's like seconds. So.
But what that raises is interesting possibility you could have a strong neutrino-driven ion, right, which is subluminal, but still it's pretty fast. And that goes out at the distance, the order of the Kelvin time times, say, 10 to the, 9, 10 to 10 centimeters per second.
You could run into that.
And then that's a target. Or that by itself going to go instabilities.
Yeah. So when we were motivating this shell of ejecta, there's various. There's outflows. Maybe if there's accretion disk around the neutron star, there's outflows. There could be early neutrino winds from the object or from the disk. So there's a lot of. And I think the point is with this calculation was just that this environment surrounding the magnetar will not be completely devoid of matter. So I hadn't really thought a lot about whether the X-rays could actually come from the interaction of this jet with matter. That's probably worth thinking about as well. But at least qualitatively, it seemed reasonable. Of course, Max Lidikov has another model where somehow the black hole is able to keep a magnetic magnetosphere even after the disk is gone. But there are several models along this line that the rotational energy of the central compact object could be contributing to the late emission. So just returning to this idea of gravitational waves, we don't definitively know that the mergers are the short GRBs. I've shown you some potential caveats. But there's another problem with GRBs relying on them as the counterparts of mergers. And that's just that they're actually fairly rare within the volume out to which advanced LIGO will be sensitive. So here I show you the histogram of redshifts with short gamma ray versus detected rate. So this is the detected rate histogram above some redshift Z by the Swift satellite. So this is over the course of 6 years. And these dashed vertical lines show you the range out to which advanced LIGO will be sensitive to binary neutron star black hole mergers. And what you see is that in 6 years of flying, only 1 or 2 short gamma ray bursts have occurred within the range of LIGO to neutron star black hole mergers, and none within the range of neutron star mergers. Now, this is because partially because Swift has a fairly narrow field of view, I guess with a tape in the sky or something. So Fermi has a larger field of view, but it can't determine redshifts. So if you say, well, what would Fermi detect if you were to extrapolate this redshift distribution? That puts you up here. But even then, the detected rate of short GRBs within the range of advanced LIGO is still pretty low, maybe optimistically, once per every few years. So if you just waited for gravitational waves and waited to have a coincident short gamma ray burst, you're probably going to have to wait a few years, which is probably another way of saying that these events are beamed, if our estimate of the true rate is correct. So the only point of this is just to show that short GRBs are great, they're easy to do, but it's not obvious that they're the only solution. So that's why I think you want to consider potential isotropic counterparts. And the basic motivation here is that there are several sources of neutron-rich matter that are ejected during the merger. There are these tidal tails I already showed you. There's also outflows from the accretion disk, both the neutrino heated winds that Chris was referring to, and also these kind of recombination powered outflows. And depending again on the parameters of the system, you can get an ejected mass in the range of maybe 100th of the solar mass. So it's long been known that as this matter.
Sorry, which parameter is that big range of ejected mass?
So I mean, I'm trying to say if you have a very non-symmetric binary, so a neutron star and a black hole. Sometimes in those cases you can get a lot of mass ejected. In other cases, people have argued it can be much less. So this is just kind of over the whole whole range of kind of possibilities. It could actually be zero, but it would require rather extreme properties. So it's long been known that as this matter expands away from the merger site, it will actually undergo rapid neutron capture nuclear synthesis. This is known as the ARC process. It was studied back in the 70s by Jim Latimer et al. And the basic idea is that you have this expanding neutrons and protons from the merger site. All of the protons and some of the neutrons are kind of fairly rapidly captured into heavy nuclei. This is from strong electromagnetic interaction. But it's so neutron-rich that there are many free neutrons that cannot immediately be incorporated in the nuclei. There are no stable nuclei with that many neutrons. So what happens is you form these seed nuclei with typical mass number about 100. And then they capture neutrons and move to the right in the chart of the nuclei. So they can only go so far before they become unstable, so you have to wait for a beta decay. And if you wait for a beta decay, that's how you move up to heavier elements. This is known as the ARC process because the neutron capture time scale is faster than the beta decay. So I'm going to show you an ARC process network. This is in collaboration with Almudena Conis and Gabriel Martinez-Pinedo. And so this is for following the trajectory of a fluid element that was kind of in a Lagrangian sense that was ejected from the merger. On this axis is Z and A, so this is the chart of the nuclei. These are the relative abundances of the nuclei. We're at T equals 0 now, so the temperature here, density here are both very high. And then as time goes on, it's going to expand away, so these will go down, and you'll see the formation of these heavy elements. And you can see, sorry for this watermark here, but you can see the abundance as a function of time up here. This is mass number versus abundance. So you see is that first we form all of these seed nuclei. Now they're capturing neutrons, so they're moving off the valley of stability. And then they're waiting for, there's a beta decay waiting point, and they all break past that. And then slowly everything decays back to stability. Now we're at several seconds, now we're at several thousand seconds. And over the course of billions of years, everything decays back. So if you want to see what the final abundance distribution looks like, it's a solid line here. This is compared to the solar system abundances. You you see these kind of characteristic peaks at A of 130 and A of 195. This is the platinum peak. I forget what the element is here. But basically, these mergers produce abundances that are actually similar to the solar system R process. And I'll come back to that in a little bit. But I simply want to say that one thing you can calculate from this type of analysis is what is the radioactive heating of this matter as a function of time after it's ejected. Because if all these decaying nuclei and they're releasing energy through beta decays and through fission, and so here is the radioactive power versus time after the matter was ejected. So initially, at very early times, the R process is going on, it's very high power, and as time goes on, the heating goes down. What this is that instead of a single decaying nucleus, which would have this behavior, you have a combination of several hundreds or thousands of nuclei decaying. So at any given time t, you're getting contributions from those nuclei that have half-lives of order t. And so it ends up producing a parallel decay. And I'll come back to this in a second, because this is how you get an optical transient from these events. So I want to briefly just mention the physics of how supernovae shine. This goes back to Dave Arnett's original explanation. So imagine I have a spherical mass of gas expanding with some mass m, velocity v, and we'll assume it has some thermal energy, which is a fraction f of its rest mass energy. And assume it has some constant opacity K. So this ball of gas is homologously expanding, so its radius is increasing linearly with time. It's a constant velocity. And its density is, of course, going down as 1 over time cubed. At any given time, it has some optical depth through the ball of gas, tau, and there's some time scale for photons to diffuse out of the ball of gas. So what Arnett said is that the emission in terms of the luminosity from this event peaks when the diffusion time scale for photons becomes equal to the expansion time scale. And the basic point is that when the ball of gas is very compact, it could have an enormous thermal energy, but the diffusion time is so long that none of it's able to escape. It's only when it's able, and of course it loses most of that initial thermal energy to PDB work, and only when it expands to the point that that emission can escape on the expansion time scale. So you can calculate the peak time scale in terms of the velocity and mass of the ejecta, and you can also calculate the peak luminosity of the event, which is approximately the amount of thermal energy this ball of gas has on the time scale of T peak divided by T peak. And this can be written again in terms of the velocity and mass of the ejecta, as well as this F parameter, which is how much thermal energy it has at the time T peak, roughly speaking. So for type 1a supernova, they have velocities of 10,000 kilometers per second, solar mass of ejecta. They peak on time scales of weeks. And you get this F from the nickel to cobalt decay. This gives you a luminosity of about 10 to the 43 Earths. For neutron star merger ejecta, the velocity is much higher, the ejecta mass is lower, so they peak more on a time scale of about 1 day. But the key thing that I think no one really addressed until our work was what exactly is the peak luminosity? What is this F parameter? What is the radioactive heating? And that's exactly what we calculated here. On time scales of 1 day, this is how much radioactive heating the matter is receiving. So we were able to nail down this F parameter and say how bright these events are. We went and did detailed Monte Carlo radius transfer simulations to show this actually works. This is the luminosity of this is for an ejected mass of 100th of a solar mass. This is the luminosity versus time. You can see that it indeed peaks at 3 by 10 to the 41 Earths per second and decays subsequently. We refer to these events as Kilonova because they were about 1,000 times brighter than nova at durations kind of similar to nova. There are other people give these things other names. We are to some extent able to calculate the color evolution of these events. The unfortunate thing is that it depends sensitively on what you assume about the detailed opacity, the frequency. And unfortunately, nobody really has calculations of, at least declassified calculations of the opacity of pure R process material. People know what it is through iron, what it is through normal elements, but this matter is like pure gold and pure iron, pure silver and pure platinum. And so we're actually trying to work with some people, I'm not, but there are people working at Los Alamos with codes to calculate this so we can get a better handle on what the predicted color evolution of these events is. I will simply say that these are detectable following a gravitational wave source. So here I show the predicted R band luminosity. The dark band is the range of these kilonova models if I vary the mass through this very wide range in the velocity through this wide range. This tells you kind of the range of their evolution with time after the merger event. And if you were to take these various survey telescopes, PPF, pan-STARRS, LSST, and to dedicate them to following up a LIGO error box, these are the sensitivities that they could reach on a time-scale of a day. And what you see is that in almost all cases, even PPF and pan-STARRS, and definitely LSST, could detect these events at peak. And the real key is that you need a search that goes deep enough, but also has a very fast cadence, so that you can follow the detailed light curve. Because really, there's no known transients in nature that have really these supernova-like transients that have this fast of decaying phase. This would be a real hallmark signature of this type of transient. I'll simply say we had one potential candidate of this kilonova. This was a short gamma ray burst. And of course, the idea is that normally after a short gamma ray burst, you see a bright afterglow. And usually the afterglow will be much brighter than this emission, so you could never detect it. We had one short gamma ray burst working on with Dan Perley, which had actually, after the gamma ray burst was finished, this was actually one with the tail. The emission faded extremely rapidly. There was no optical detection in about a day or a tenth of a day after the burst. But then about a day later, he noticed it was optically rebrightening. We actually followed it over the next several days with the Hubble Space Telescope, next several weeks. And it had a light curve that was qualitatively consistent with being one of these kilonova coming from an event that produced a short gamma ray burst. The unfortunate thing is that when we looked at the Hubble imaging to see, so I should say the model made a prediction about how far away it was. And the prediction was it was about redshift 0.2, maybe a fudge factor of a factor of 2 there. Well, maybe not that much, but the fortunate thing was that there was no galaxy at that location. There was some galaxies nearby at lower redshift. There were some smudges that could have been at really high redshift, but it wasn't clear. Maybe this event was one of these merging neutron stars that was kicked out of one of these galaxies, and maybe that's why it had no afterglow, because it was in a very low density environment. We don't know. So this is unfortunately not a definitive case. Maybe this was a kilonova, maybe it was a weird type of afterglow we don't understand, because we had no redshift to confirm the overall brightness. The final thing I'll say about these is that they provide a potential direct probe of the origin of these R process nuclei. So despite what you may have read in your textbook, we actually don't know where these nuclei come from astrophysically. All the elements shown in blue, they say they're from supernova, but that's more empirical than theoretical. Our actual current models of the outflows from newly formed neutron stars, which is where this was thought to be the site of the R process, don't actually work. The neutron star mergers do work, but we don't know if they occur at the correct rate or if they occur early enough in the chemical evolution history of the galaxy to explain the fact that very metal-poor stars have a lot of these elements. The mergers are expected to be delayed. So the point of this is, though, if we went out and detected or put constraints on the rates of these kilonova, how bright they are and how frequently they occur are directly proportional to how much they're polluting the galaxy with these types of elements, or galaxies in general. And so actually you can show that a survey like PTF or even LSST can really nail this down. If it doesn't start detecting these kilonova soon, given a short cadence survey, it can really tell you that these mergers can only be contributing some fraction of the R process elements in our galaxy. In other words, this is very similar to what you do with type 1a supernova to understand iron production in the universe, but applied in a slightly different context. So, given the time I have left,
Can I just ask you one question? Just, you were making the case that the outer parts of the disk are ejected by alpha particle recombination. But what I'm wondering about is how persistent that is, because there's a radius, characteristic radius at which the alpha particle, this country gets low enough that alpha particles recombine, right? Now, I would think that radius would tend to move inward as the disk disperses and it gets cooler.
Yeah.
And that there would be then some finite amount of material that would remain inside the radius where the alpha particle wasn't large enough to eject. So once the alpha particles recombine that stuff, then it would tend to
you started a new evolution.
You start a new evolution, and you have some continuing, late accretion on the black hole. Now that's not much stuff, much less than the phase that you're describing, but a specific energy that's released associated with its accretion could be much, much higher.
Yeah, so I think the idea that it
That might
completely
sense.
disperses the disk is incorrect. There will be some matter close to that remains bound. And this is actually something that I really want to look into. I want to look into with 2D simulations following the longer term evolution to understand. Because like how much remains bound, how far does it get ejected out? Is there some matter that gets ejected far out and then falls back? So yeah, this is really, I think, a very interesting question. And I agree, not all of it will land down. I'm just saying that.
No, I mean, I understand,
yeah,
but
yeah.
you know, you're dealing with huge differences in efficiency, but that's why.
Yeah, exactly. So if you've got a very high efficiency at late time, you can get of course, then you have to understand why some of them have the tails and some don't. They could be efficiency. So for the remaining time, I wanted to describe some more recent stuff on white dwarf neutron star case mergers. So there are actually 4 white dwarf neutron star binaries in our galaxy with merger time less than Hubble time, so similar to the number of neutron star mergers. You can again estimate the rates. It's highly uncertain. This is the lowest estimate based on not correcting for pulsar beaming. It's probably higher than this, but they're in the range or maybe slightly higher than that of binary neutron star mergers, but this is all very uncertain. But the point is that they potentially can merge at a comparable rate. These events, unfortunately, will merge out of the bandpass of both LIGO and even potentially LISA, whatever the space-based thing that will hopefully eventually fly. So you can't play the same game with LIGO of looking for a merger and then following it up. But nevertheless, if we did have something like LISA, it would give us a much better census of these mergers in our galaxy and allow us to pin down this merger rate much better. So when a white dwarf merges a neutron star, the potential outcome is actually more complicated than in a neutron star. It's not even obvious it will produce a very violent event. This depends on the mass ratio of the binary, whether the mass transfer is stable or unstable. So the white dwarf is moving in from gravitational radiation. At some point, it starts to overflow its Roche lobe and transferring mass to the neutron star. The question is whether that mass transfer is a runaway process. And this, I don't want to go into the details of this. I'll simply say that for low mass ratio binaries, it's more likely to be stable with mass transfer. It just means the white dwarf will slowly accrete onto the neutron star over the course of millions or billions of years and just slowly back out as it expands. And this can be a source of ultra-compact X-ray binaries, but it's not a particularly violent event you can see from very far away. But if the mass ratio is above a critical value, say between 0.2 and 0.5, then the mass transfer is unstable. A little bit of accretion leads to more accretion, and you end up disrupting the white dwarf into a torus around the neutron star. And these kind of characteristic radius of this torus is of order 10 to the 9 centimeters. So it's slightly similar to the radius of the original white dwarf. The interesting thing for me is that the composition of this torus, the mass is whatever it was of the initial white dwarf, and the composition is whatever it was of the initial white dwarf. Depending on, you can play with this and get various white dwarfs being disrupted. So you can again play this simple game and estimate what is the accretion time scale. And it's quite a bit longer than the case of neutron star mergers because the disk is more extended, more like minutes or hours. But the accretion rate is still very high. It's still in this kind of photon trap regime. And this led Chris Fryer to propose that these events maybe give rise to some long-gathering disks. I was actually interested more in the structure of this accretion disk because I found it very interesting that you have this fuel and you're feeding it into a compact object. So basically nuclear fuel. So what I did was the simplest thing possible because the group in Illinois has done a few calculations of this, but really there's been very little work since Chris Fryer. And so I started out with the simplest thing, which is a one-dimensional time-mapped steady-state model of the accretion flow. The novel thing that I did was I included the evolution of the nuclear reactions. So I included the fact that as matter is flowing in, it can get hot and start burning to heavier elements. And so in these types of models, at every radius in a disk, you have to balance heating with cooling if it's in steady state. So the heating is not only supplied by viscous turbulent dissipation as in a normal accretion disk, but also has a component from nuclear burning. It can also be cooling. And the thing about these accretion flows is that they're known to potentially be susceptible to outflows from the accretion disk because they have no real source of cooling. And so they tend to be very thick, marginally bound flows. And so what I did is I allowed my accretion structure to have an outflow, a mass loss rate from every radius in the disk. And I determined that mass loss rate by demanding that two things. One is that the cooling of that wind offset the other forms of heating in the disk. And I also demanded that the disk as a whole be marginally bound with the Bernoulli parameter in the midplane less than 0. I'm not sure if this is totally physical, but it allowed me to move forward with the calculation.
It's basically like what's the Blanford and Begelman did?
Yeah.
But then including nuclear.
Yeah, it's kind of a Blanford and Begelman with basically allowing the nuclear burning to enhance the mass level. So here's some example solutions. I don't want to get into too detailed. This is a carbon-oxygen white dwarf, helium white dwarf. This is just the temperature ratio of radiation to gas pressure. Mass accretion rate, which actually goes down with radiation because you're losing mass to the winds. The interesting thing is if you look at the ratio of various sources of heating in the disk, for instance, the source of nuclear heating to viscous heating in the disk is a function of radius. Where you get to radii in the disk where nuclei burn, I'll show you that in a second, you get this kind of spike where the nuclear energy can actually become comparable to that released gravitational energy. In the case of a helium white dwarf, it's a very large peak. And this means that the nuclear burning can have some effect on the stability and structure of the accretion flow. So I gave them this, I like the name for this, it's like nuclear dominated accretion flow. It's not really dominant, but it gave me a catchy title. Nuclear burning is important. So here's the composition of the disk. This is the mass fraction of various elements versus radius. And the picture I have is you're feeding in carbon-oxygen material. You get into a certain radius. It's quite low temperature initially, but then it heats up. You start burning the heavier and heavier elements as you go to smaller radii on the disk. At some point, you have a narrow region where you produce iron and nickel. And then interior to that, you get so hot that you photodisintegrate to helium and then eventually free nuclei, and then those are what settle onto the central complex.
So do you have witness where you have the association?
What's that?
Do you have a cooling?
Yeah, this is actually a cooling source. Yes, there's actually a source of cooling there.
So is there room in those space?
I only model it down to where the dissociation of helium is just beginning, but I include that. Yeah, there's still a wind. It's just that. Yeah. So it becomes less important because you have this source of cooling. So in the outer parts of the disk, it's carbon oxygen that you go in and you see burn it. The point is that the nickel is actually restricted to a fairly narrow region of the disk. So if you know the mass loss rate, you know the mass fraction, you can kind of estimate what fraction of the wind is lost in various elements. As you might expect in these models, most of the mass is lost from the outer parts, so it's unburnt carbon and oxygen, but you go to heavier elements. I found that only maybe like 1% of the outflows will be nickel, 56. But I did find that in these models, the generic feature is that a lot of the mass of the initial white dwarf is actually lost. So maybe like 80% of its initial mass is lost in an outflow. So even a percent of nickel 56 is not an extremely low amount. So to wave my hand even further, I'm going to try to motivate that it's not unrealistic to think that all this ejecta, even though it's coming from different radii than it is, it might ultimately all end up in some kind of homologously expanding blob of material. So the basic idea is that just as this disk forms, the time scale is much less than the viscous time. You're going to have some outflows from the disk, but they're going to occur at kind of the dynamical time scale, the outer cover of the disk. You haven't yet even had really the matter that's flowing inwards yet. It's just kind of right after the destruction process. But you're going to have some outflows, and then they're going to have some time to encase the system, and then maybe you're going to get outflows from the inner parts that have faster velocities, and maybe they'll somehow not run into this material. So maybe at the end of the day, you have, your kind of some shell matter moving out. Of course, realistically, the nickel could get out, and the middle, and it could be probably very spherical. But for purposes of calculating optical light curves, you need the velocity and the mass of the ejecta and the amount of nickel produced. And you can kind of get that from these. So what you find is that, using this very simplified model, that there could be 4 types of subluminous supernovae. So these events typically eject lower nickel masses than a normal type 1A supernova. Normal type 1A might eject half a solar mass of nickel. These are more like 100th or even 1,000th of a solar mass. But so what I was finding is as I went to more massive white dwarfs, I tended to get larger nickel masses. So you can calculate the light curves you might get from optical transients. And they tend to be quite a bit dimmer, but all kind of peaking on timescales of weeks. A week, weeks. So kind of somewhat shorter lived and somewhat dimmer than type 1A. And I'm not going to claim that these events are any observed astrophysical events, but I will simply say that there are a class of events now. These are actually several classes of events. These particular ones are referred to as calcium-rich transients. They're unusual for a few reasons. One is that they evolve very rapidly. timescales are weak. They tend to be somewhat less luminous than a normal 1A supernova. But the weird thing about them is that they all occur, at least a lot of them occur very far outside of the galaxy. The Monsi-Kalispal tells me that she claims that there are basically none that occur in a distant galaxy. It's probably like a sample of maybe 5 or 6, 7, or even 10. And so this is kind of unusual. So, you know, if you had a white dwarf neutron star binary, maybe the system will get a kick when the neutron star supernova forms, or supernova. So maybe these events could happen outside of the galaxy. I'm simply motivating the fact that there are transient surveys detecting events that it would look like these. So I'm going to finish just by saying that, you know, this was a very simplified disk model, and there's a lot of things I worry about. If the nuclear burning is contributing an appreciable fraction of the energy, is the torus going to be thermally stable, or is it, so in other words, is matter going to accrete in and just kind of steadily burn and continue to accrete in, or is it going to burn it, setting it and blow up? And this is the kind of thing you really need to do a hydrodynamic simulation. So I'm beginning some work with Rodrigo Fernandez at the IAS to do axisymmetric hydrodynamic simulations. We're not doing the merger itself, we're just starting with a torus of matter that we think represents the properties following the merger. We try to achieve parameters that the merger, that the torus can form without burning the important during the formation process. And so far, I'm just going to show you, we've only got like one reaction. This is a very low resolution simulation as well. But I'll show you. So we have one reaction. This is a pure carbon torus. This is the radius. This is the central object. You see a neutron star. And these are density contours. And the color you'll see is the fraction of magnesium being produced by this reaction. So it's initially it's pure white, which means it's pure carbon oxygen. But then, you know, as matter starts to accrete, we have, you know, this is very low resolution around the poles. But you start to get this structure where you start getting matter in and it starts burning. And you start getting these kind of ejections of material. Sometimes it's kind of convective, and you get these kind of at the end here. I think you get this is actually run for basically only one orbital time at the outer edge. We haven't even followed an entire visiting time.
What's the smallest radius you can see and resolve into?
Well, we go down to about equivalent about 10 to the 7 centimeters, so about 10 neutrons per radii. So I think for this calculation. So stay tuned. It'd be very easy to implement a full reaction network into Flash once we get it going.
So is everything that burns getting it back?
No. Generally what happens is...
Because I don't see much color in the torus.
Yeah, well, okay, so this is really, it should be blown up. But basically matter is flowing in. I mean, typically what one finds is that you do have matter flowing into the inner boundary. And the point is that the torus is not colored because the burning is being restricted to very small radii. So this is all pure carbon. It's just that there's not a lot of diffusion of fuel upstream. Is kind of the way it's saying. There's not a lot of matter that is being burned that doesn't escape from the grid is coming out on the poles. Of course, whether this is actually inbound or whether this is part of some larger scale convective structure is something.
So how do you do your calculation? Is this an MRI?
No. This is with Flash, and we have just implemented an anomalous alpha discussor. So
you don't have diffusion of matter that might go along with the alpha?
No, to the extent that taking a stress tensor proportional to pressure, to the extent that restriction does give you turbulence, you could have potentially a mixing. I mean, it's just that you're not fully capturing the details of the nation turbulence.
What do we do with the inner boundary? There's much more energy released there, or anything than that.
Well, our hope is that we're going to go down to the radius at which the photodisintegration happens. So the hope is that you're kind of the matter leaving the inner boundary will either be cooling at that point, in which case, or be already free nuclei. So we're trying to go down to small enough radii that there's not a lot of more nuclear energy coming out.
Neutron star, there's still a lot of energy.
Yeah, so there could be, if you had a jet or something from small radii, that could definitely feed back on the floor. Yeah. So anyways, we're hoping to see. I'm not too much away other than to say that we're still trying to work the bug out, but it isn't obvious to me that in all cases this is kind of stable accretion and burning. It seems like there could be some regimes.
What the calculation has been done so far, what fraction accretes, what fraction gets ejected?
Generally, what we find is that we find the standard thing, which is that m dot kind of decreases linearly with radius or something like that. So nominally, I would say, given the outer radius of 10 to the 9 centimeters, inner radius of 10 to the 7, I would say maybe 99% is being pushed, being pushed out on kind of this polar region. Whether it's actually unbound or part of a larger convective eddy, I don't know. But I'm thinking that it's a high fraction. So I would say at least between 90 and 99% is being lost. But this is a subtle issue because of how you're feeding this outflow.
Well, the other issue is how you set this up, because when the white dwarf first begins to transfer mass, some of that can go quite deep in the gravitational potential of the neutron star. There's the accretion stream solution, and it spirals around, forms a very compact disk, and I think that disk initially is compact enough that the carbon atoms just associate them and it remains bound.
Right.
Which would then provide a very powerful source of free energy for, amplifying the field, for example.
Yes.
And so, even if you accrete a few percent that way, which sounds quite plausible, that's like what?
Principle,
huge feedback.
Yeah. So it depends on what.
So how you set it up may strongly influence what you.
Yeah. We're trying to take the most extreme mass ratios that allow us to be in this unstable regime. But I agree that the initial accretion stream has much lower angular momentum than the bulk of the system. And I don't know exactly how we'll be able to do that. I mean, currently our idea is just to set up a torus that has basically the angular momentum and energy of the initial orbit.
Well, and that's simply you can't really do it.
Yeah. So I don't know. We could try to put some type of central luminosity or something. The hope is that energy will come out the path of least resistance. So I agree. Ultimately, one would like to actually do a 3D SPA simulation or something. I'm kind of interested more generically because I think that this could have applications beyond just these events. I think it could have applications to collapse star accretion, just massive stars collapsing, and if they have a substantial amount of angular momentum around the black hole, this could be important. This actually was a way that I think back in the early 80s, Stan Windley was discussing, before they knew how supernovas flow, they still don't have supernovas flow, but they're discussing extremely rapidly spinning stars that basically they centrifugally hold up with the explosive oxygen burning. So this may harken back to some very old work, but I think it's relevant. Okay, I'll just conclude very general conclusions. I think wide field survey is discovering new classes of transients. I think now it's time to evaluate the counterparts of known astrophysical events that maybe we haven't considered very much. I think the first second gravitational waves will arguably be one of these neutron star binaries in the next 5 years. It's very important that we identify a counterpart. For the neutron star mergers, short GRBs seem a good option, but I don't understand the origin of these late X-ray tails, and also they're rare enough that we can't expect to have, several coincident detections with the gravitational wave per year. So I think you have to look for other things. I think these optical transients are a promising source, because I think it's hard to avoid ejecting some neutron-rich matter during these movements. But it requires rapid follow-up, and you have to be able to identify these sources in a very busy field of optical transients. The Wedge Venus emergence occur at a similar rate, but they've been studied far less. I think that the outflows will give rise to some type of optical transient. Could be related to subluminous type 1 supernova, but really we need multi-G simulations to understand this interplay between the burning, convection, outflows, etc. So I'll finish there. Thank you.
More questions for Brian?
Now it's up to the observers.
Yeah, right. They have to go minus. Oh, here.
Okay, so this is different than what you were talking about. Do you know how far away current neutrino detectors can see a neutron star merger?
My understanding is that they don't produce a lot more neutrinos than a quark clock supernova. So I think it would have to be. I mean, the current underground detectors, I guess, would have to be within a few megaparsecs or something. So it's probably a pretty rare occurrence. We're probably more likely to detect a quark clock supernova.
Not that much better than it used to be for 1987-8, I think. So still local group.
Yeah.
At most.
Yeah. Like I said, there might, I think that these are. I don't think these are even as much as a normal quark clock.
In the magneton model for the extended entry tails, what causes the initial spike, which is very separate?
It's a very good question. I mean, so I'm waving my hand and invoking two mechanisms. I'm saying I want the time scale from the accretion disk, and I want the time scale from the matter structure. So I'm saying that there's an accretion episode onto the neutron star on the viscous time of the disk that powers the gamma ray. And I'm saying that,
energy of the magneton.
what's that?
Then the tail is produced by.
And then the tail is produced by the spin down of the central object. So there's a big problem with this, which I didn't admit to, which is that the environment in the first second is very heavily loaded with baryons. It's very hot. This proto-neutron star, or proto-magneton, or whatever it is very hot, and it's driving neutrinos off of its surface. And how relativistic a jet could get in that first second is limited by that baryon loading. So I think this is a problem. It depends on exactly how the early hypermassive neutron star is cooling, what time scale it's cooling.
But you can actually turn that around because there is potentially interesting time scale associated with that stuff coming off the thin sky.
Okay.
Right. So, how it organizes itself, whether it gets squeezed from something coming behind and so on.
Yeah.
It's not easy, but there is a more extended time scale for mission. You get just from the past year.
Yeah, my argument is always that, I don't think you need a black hole to necessarily make a jet. I think there's ample evidence in nature that creating neutron stars. Also, Circinus X1 supposedly has a microquasar jet with gamma 25, and that's an accreted neutron star. So I personally, phenomenologically, I think that it's fine to invoke a jet from an accreting neutron star. Whether that jet is relativistic enough, is important.
Do you understand why you're saying in the case of Tidal disruptor around the neutron star, most of the materials are rejected by this additional effect of nuclear burning?
I don't think it's actually just, I think it's a generic consequence of these types of outflows. The nuclear burning would enhance, so the basic point is that you're forming a torus that is hot and it has no cooling mechanism. So the photons can't cool it. It's not compact enough or hot enough for neutrinos to cool it.
So even if you don't have a nuclear part?
So even if you didn't have the nuclear burning, people, Blanford and Bangelman would argue that you could get outflows from the disk. It may depend on the initial conditions of the torus.
We just had Sasha Tchaikovsky, and he started with the torus at about 100 gravitational waves, something like that. And he was commenting, that he wasn't seeing a big Blanford Wavelength type outflow distributed over radius. I mean, it's true that when these got in, right, there was this wind moving up along the sides of the funnel that was driven by image processes occurring, around the ISCA.
But it wasn't
the positive really constant type effect that these guys are focusing on.
Right. So I think for purposes, the interesting thing for me is not necessarily to believe the calculation itself, but to see what the changes are with the nuclear burning. If it's a big effect, then you might argue that, in my models, it was a fairly substantial effect. So what was funny, was interesting, was actually, I thought the burning would be more heavily concentrated in the midplane than the viscous heating. Yeah, it's very temperature dependent. What's happening was matter was kind of coming in the region where it's important. Matter was coming in. This is just based on some preliminary looking at some of the stuff Rodrigo was doing, but it was coming in and it wasn't instantaneously burning. It was actually taking a finite amount of time to burn. So a lot of the heating was actually distributed a little bit off. So that's the kind of heating profile you want to drive a wind. Is one that distributes the heating in low density regions because you get an entropy and rise and you get it. So it could be that the nuclear burning could contribute to the outflows.
Okay, well, we can continue the conversation. There's over cookies. Tonight we'll be taking Brian out for dinner, and I'll send it